Matt. Thank you, Peter. Our next speaker is Matt McLeod from Stockholm University, and he will be talking about the full multi framework for modeling the fate of plastics in the aquatic systems. So Matt, the floor is yours.
Thank you, Jing. You're seeing my slides, I guess? Yes?
Yes.
Very good. Yeah, thank you very much to the organizers and to everybody who is hanging in on the fourth session of the workshop, and also for the last talk of this session. It's really my pleasure to have the opportunity to tell you about an ongoing project. So what you're going to see today is some of the first results that we're showing publicly from this open source, multi-species, multi-size, multimedia framework that we are developing for modeling the fate of plastic in aquatic systems. I want to start by introducing the whole team because I'm making the presentation today, but actually when we have the discussion session, Prado and Antonia will also join, and they'll be more qualified than me to answer some of the questions perhaps, and certainly qualified to participate in the discussion at the end of this talk. I am a professor of environmental chemistry at Stockholm University. My background is in chemical fate modeling. So I got involved in this project. Actually, Antonia invited me to collaborate with her. Antonia has worked for many years on modeling nanomaterials in the environment. And the person doing the actual work and doing the coding is Prado, who's been working with me as a postdoctoral scientist at Stockholm University for a little more than a year now. So our project, of course, the other important partner in any project is the people who are providing the funding. And in this case, it's SETAC through their Long Range Research Initiative. And we have a really active and involved liaison team from SETAC who've been giving us really good input and helping to shape some of the questions and development of the project as we've gone along. Our mandate in this project, which is a 2-year project that's now about a year and a half into, or a year and a half in progress, is to develop this open source modeling platform for exploring the environmental fate and transport of plastics in aquatic systems, and eventually to support the use of models for estimating exposure concentrations in risk assessment. But I'll talk a little bit at the end about where we see real good opportunities for applying this model framework in a whole bunch of different ways. So what do I mean? The title of this talk was supposed to illustrate that our goal with this framework is to address the full multitude of different dimensions of variability that are possible when you talk about plastic pollution in the environment. So the first of these multi-dimensions is multimedia. And this is an example illustration that I'm going to use to build up our model framework for a large lake system, where in this case, the multimedia actually, I guess if you're strictly speaking, would be just the sediment and water interface. But actually within this lake system, from the perspective of the fate of plastics, there are different compartments within the water column that also can have influence or that have different characteristics that influence the fate of plastics. So within a large lake system, or the generic large lake system that we're developing as part of our model framework, we differentiate between the surface water where UV exposure is higher, which might facilitate degradation and more rapid fragmentation of plastics. The epilimnium that would be in rapid circulation with that surface water where there is light penetration, and then the hypolimnium of the lake, which is further down, deep, dark, perhaps different processes going on that influence, or different process rates that affect the aging and behavior of plastic. So into this system, we introduce input of plastic, and in the generic scenarios I'll show you later for the modeling, we introduce plastic as in the microplastic range, about one, or in that case, a uniform 1 millimeter fractions of plastic. But in general, you can introduce plastic in any size range that you like. In this lake scenario, we imagine that this input is occurring through rivers or wastewater treatment plants or something like. And we heard from some of the earlier talks today also about direct land runoff into lakes and rivers as a source. That plastic is then subject to fragmentation processes. We just heard a description about this, that plastic, once it's in the environment, begins to age, and because of physical and chemical stress, we can wind up with fragmentation into smaller size fractions. So that's the multi-size aspect of the modeling framework. All of those different size fractions are then also subject to what we call speciation in our title. This means all of the virgin plastic that you put into the system, or plastic products that can fragment into smaller sizes, these can also have biofilms grow on them that colonize the surface, or they can heteroaggregate, we call it, with organic carbon. And all of these, both of these heteroaggregation and biofilm formation processes change the properties of the plastic or of the aggregate that the plastic becomes a part of. So it has a different effective density, it's shielded from UV radiation, it's maybe more or less likely to participate in heteroaggregation once it has a biofilm upon it. All of these things are, or this weathering and colonization process by biofilm or aggregation into with organic carbon. This all has the potential to change the fate of the plastic, whether it is settling into the sediments or floating to the top, the rates of fragmentation. So within our model framework, we keep track of these 4 species, what we call virgin microplastic or free microplastic, microplastic in heteroaggregates, microplastic with biofilm on the surface, and microplastic which is heteroaggregated and with a biofilm process, and with biofilm on it. So that builds up the entire full the multi-species, multi-size, multimedia framework for modeling plastic. This has all been illustrated so far just for a lake system. But we're also then take that unit cell for the lake and have adapted it to describe different systems. The one that I'll illustrate later in the talk is for a generic river model, where we put segments with all of these different processes and size fractions described together to form a linear river. Now we change the definition of the water cells a little bit. Rather than a hypolimnium or epilimnium, which is present in large lake environments, we have now surface water still with high UV penetration, but then flowing water, stagnant water right above the sediment layer, and again, interactions with the sediment. But within every one of these water cells, we have opportunities for all of this fragmentation, biofilm formation, heteroaggregation processes that I was talking about before. This river model is up and running, and I will show you results from it in a second. We're also currently working, and within the frame of the project, we will adapt this unit cell again to describe the surface of the oceans, or perhaps the mixed layer of the oceans, to do and integrate it using ocean transport descriptions from the Better Global Contaminant Fate model. So this is something that's ongoing now, which will also be eventually released through our open source website that I'll describe also later on in the talk. So we've heard a lot now from other speakers about one of the challenges in putting together a model system for plastics is that you need process descriptions for your models. And Ken said right at the beginning, when you sit down to write a model, one of the most important things is to understand the state of knowledge for all the processes that you want to describe. And we also started with this point, but already when we started this project, the goal of the project was to create a modeling platform that could be refined as time goes on, and to make it open source so that all of these process descriptions can be refined as new science is being done. And this is recognizing really, I think, what all of the speakers have been talking about today, which is that when we're working in the microplastics field, or in the plastics field in general, we're working in an area where there's lots of new work going on all the time, and new insights into processes and new discoveries about where you find plastic in the environment and in what amounts. So our goal here has been was to make a review of the literature and put in reasonable best estimates of process descriptions, or reasonable useful estimates of process descriptions into our framework for testing purposes, but then to open source the whole framework and make it available to everybody to put their own process descriptions in and test what these mean for the description of plastic fate that the model provides. So just quickly, I'll give you an example, or a few examples of some of the process descriptions and literature review work that we did to do our initial parameterization of the model. Here's an illustration of one of the bits from the model that I talked about earlier, this process of heteroaggregation and heterodisaggregation, and then also the potential for homoaggregation of particles into agglomerates in the environment. This homoaggregation process is something that was lots of it, or generated a lot of interest in the nanoparticle fate field that Antonio was working in, or has been working in and continues to be active in. And here's an example of 4 papers from the literature that describe different aspects of this heteroaggregation or heterodisaggregation process that went into our selection of equations for our modeling. Similarly, for biofouling and the potential for growth or for biofouling growth upon the surface of microplastics, we have an emerging literature. We have some old literature about marine algae growing in general on surfaces, and then a more contemporary literature that looks specifically in the context of microplastic and for microplastic fate. And then finally, a really interesting one for me is these process descriptions that describe weathering and embrittling of plastic, and then fragmentation in the environment that generates smaller and smaller size fractions of plastic over time while the plastic is resident in the environment. And this is an area where there's lots of interest and lots of studies, but where it's actually very difficult to bound estimates of the timescales for this weathering and fragmentation, especially for small particles. As you get smaller and smaller down the size fraction, there gets to be a question actually of what the energetics required to fragment very small particles would be, and whether this is a process whether fragmentation is the right description of this process, or whether it's an erosional process at some point. So we have, based on our literature review at least, we have put in a first description of all of these processes to make the model framework run. But I want to stress what I said before. All of our process descriptions that we suggest in the model framework, or that we've integrated into the model framework at this point, they're intended to be edited and updated by a user community for of this open source platform, incorporating new information and understanding, and recognizing that this is a rapidly evolving scientific field. What the model framework does is takes all these process descriptions where you distill your understanding about these individual processes into first order rate descriptions of the competing processes. And then the model framework synthesizes this into the mass balance equations for every model cell and solves these first order differential equations. The software exists in the Python programming language, so it takes advantage of fast ODE solvers that are available in Python. So what I want to do is give you an illustration of what this means, or what output from this model looks like when you are considering all these different dimensions of variability and evolution of plastic contamination in the environment. And the case that I'm going to show you is for a 1,000 kilometer long generic river subdivided into 20 river segments that are each 50 kilometers long and 80 meters wide. This river has a flow velocity of 1.3 meters per second. All of these parameters are taken to roughly correspond to the Rhine River, actually. So that's where we got these the initial parameterization for this generic river, and then we just generalized the whole thing to make it uniform in width and in flow dimension, really to highlight in these illustrative case studies how the differences in density and different assumptions about these model parameterizations affect the behavior of plastic in the system. So what I'm going to show you is illustrations of the concentrations of plastic along this river for emissions in the first segment of the river of 1,000 micrometer diameter spherical plastic particles. So here's the first case. Low density microplastics, imagine this to be polyethylene with a density of 980 kilograms per cubic meter, so slightly less dense than water. Just what I said, imagining 1,000 micrometer particles emitted into the flowing water compartment at the beginning of the river. Just to start, I want to show, because I want to build this up a little bit, and I hope everybody's internet connection is fast enough that you're seeing the animation here. So this is just to start an illustration of these free polyethylene microparticles just in flowing water as a function of distance going down the river. Here in the bottom as a function of distance going down the river. And the concentration expressed in number per cubic meter. What you see initially, remember the emission is being made in the 1,000 micrometer size range. So that's the green line here. You see initially quite a rapid decline in this 1,000 micrometer size range. This is due to dilution into the system and also transformation of these emitted particles into different species and fragmentation into different size fractions. The animation here is illustrating an evolution in time. So we had a little discussion before about time lags and how everything considered whether or not a system is at steady state is a key assumption to understanding whether what you're seeing is a long-term average condition or some condition that still reflects an influence from the emissions. Here we're illustrating this whole thing. So we start the system with no plastic in it, start this emission, run it for 1 year of model time in order to come to something that starts to approach steady state within the river system. So that's what you're seeing counting up in here and the time variability that's going on. So that's just for the flowing water compartment in the model. I'm going to put that here on this next slide and then add the other compartments that make this a multimedia assessment of the fate of polyethylene. So now I've added the surface water and the flowing water and the stagnant water and the sediment. The first thing maybe to notice in this is that there's no polyethylene entering the sediments. This is because the density of this plastic is less than the density of water. So these free virgin microplastics don't enter the sediment at all. You see the plastic moving up into the surface water and that is actually where the highest concentrations come. I'll show a little quantification of this in a minute. And then also much lower concentrations down in the stagnant water layer, which is closer down to the sediments, again, because this is a low density plastic. So this is all now for the free microplastic. We also have the heteroaggregated species, which represents plastic that has been attached now to particulate organic carbon within the system. This is actually the dominant species in this model parameterization. So you see slightly higher concentrations. I should have mentioned right away, we're always dealing here, just so that we can see everything all in one set of plots with a log scale of concentrations on the vertical axis. So what we're seeing actually is the dominant species in the system are these heteroaggregated polyethylene species up in the surface water compartment. Here is the biofilm covered species, and then finally the biofilm and heteroaggregated species. So I took a little bit of time to build up these plots because I think in the end, Prado and I counted that we have in these plots that you're looking at now, how many? I think it is seven. I think it is seven dimensions of variability in terms of there is space, there is time, there is size fraction, there is species. What am I forgetting? There is there is media, and there is one more. But that's why I took a little bit of time to build this up, because this is an illustration of this full picture of all of these possible fate pathways modeled for this individual plastic. So this is just to add the last dimension to this. Oh, here's the last dimension, actually the sixth dimension, illustrating the summary of the different amounts or the prevalence of the plastic, the number of particles of plastic. First of all, across the top in the surface water, integrating across all the different size fractions. So you see by the end of the simulation, greater than 95% of the plastic, of this low density plastic, is in the surface water of the river. And then also across the top, integrating over the different species of plastic, where I mentioned before that the heteroaggregated plastic was the dominant species in this particular simulation. So that's the polyethylene case. Here's a neutrally buoyant, this is kind of a hypothetical scenario, but if you imagine something like a polyamide plastic that can have densities very similar to that of water, here's a neutrally buoyant plastic with a density of 1,000 kilograms per cubic meter, now jumping to the end with all of the different dimensions illustrated. One of the main things to notice about this, one of the main differences now compared to the low density plastic, is you see this green line that represents the 1 millimeter plastic that's emitted into the flowing water in the first compartment. This just goes linearly or uniform, not linearly, but linearly in log space down as you move down the river. And this is because of what Peter was talking about just a second ago. Even this neutrally buoyant plastic, it tends to settle and sink into sediments. And we have actually in this preliminary parameterization quite a quick burial in sediments within the river. So what you're seeing is that initial release of the 1 millimeter plastic basically sinking like a stone into sediments where it gets buried, but not before it fragments a little bit into smaller size fractions and also begins to get, and those smaller size fractions are then transported down the river and undergo heteroaggregation and biofilm formation and these other fate processes that I was talking about. And then at the end of the density scale, consider something like polyvinyl chloride, PVC, with a very high density, much higher density than water, now 1.6 grams per cubic centimeter. Now what we see, one thing you see actually now is some jumping in the plots, which represents some numerical challenges that the solver is facing with very fast process rates associated with this parameterization. But after the calculation stabilizes a bit over long times, what you see are both of the two largest size fractions, the 1 millimeter and the 100 micrometer, are both now settling into the sediments and being removed. And we only see the much smaller size fractions, the 10 micrometer, 1 micrometer, and 0.1 micrometer being transported down the river. So this is again similar. I see you, Todd, I'm right near the end. This is again similar to what Peter was saying about settling of high density plastics close to sources rather than being transported. So just quickly, one of the things you can do with this is and we heard before from one of the other speakers, when you have a model, it's important to do something for performance evaluation. And I want to also highlight as an example of hypothesis formulation. This is a a picture from a paper by Cui, Murrell, and Coleman's, where they analyzed measurements from the environment of the relative abundance of different size fractions of plastics in all kinds of different systems. And they found quite consistently within a size range, a log size range between 1 and 3 of these log micrometers, so up to 1,000 micrometers. This linear relationship of the log of relative abundance versus log size. And in our model simulations for polyethylene and that polyamide, the buoyant and the neutrally buoyant plastic, we see something similar to that, even in this very generic system when we look at the end of the river and after 1 year. Interestingly, we model size fractions much smaller than you actually can observe in the environment with current technology. And so the model provides then some estimate of what this relationship might look like for much smaller size fractions as you look further down in the size range. So this is an example, I think, of using this kind of model framework for hypothesis generation and for driving future research that you might be interested in doing. So all of this code is up and running, and it will be open sourced. We're planning on public release accompanying our first paper about it, which is in preparation now and should be coming soon. But if you have a GitHub account, I'd invite you to just text or send a message through to Prado, and she'll invite you to join the GitHub repository as soon as it's available. And just in final, I just wanted to end with a little comment about possible uses of this. I think in addition to doing bounding exposure assessments or bounding estimates for risk assessment of exposure, this kind of framework is really useful for hypothesis generation and scenario analysis, for helping to make for helping to target research on questions that will help us to limit uncertainties on our descriptions of plastic in the environment. Sorry for being a bit too long there, Todd.
No, perfect. It's all good. It's just trying to keep everyone on track, and I think we've done a great job. So compliments to all the speakers in that regard. And we do have time for questions as well. So I think one question that came up, you mentioned Bart Coleman's paper with the different probability distributions, and you multi-model addresses size, different types of polymers, but do you also address shape as part of that and the influence that shape might have?
This is an interesting question. We want to. We have not in the scenarios that I showed and that we compared to Bart's paper there. These we're modeling spherical particles. We can consider it. I mean, the framework is totally flexible, so you can consider different shapes. The big difference in terms of shape determining fate has to do with how quickly the particles will settle, and the physics associated with settling through water columns, for example, is one of the big differences. And definitely there are papers about this, and you can drop in different descriptions of this. We played with this a little bit, but at some point we decided that we're not experts on fluid dynamics and the influence of particle shape on settling across different sizes. So at some point we decided it wasn't up to us, but that we would that it was up to the real experts on this to try putting their models into our framework eventually to see how these differences affect the fate or the interesting things about the fate that they're interested in modeling.
Right, and I think there are a couple of questions somewhat related to each other, and it might relate to sort of these underlying assumptions that you have within the model that you're working with and how it influences the results that you're showing. And in particular, what is a question coming up is around the role that the biofilm plays in terms of influencing density. And it seems curious why the biofilm doesn't seem to have an impact in terms of transferring the particles to the sediment, at least for polyethylene, as you simulations seem to show no uptake to the sediment.
Yeah, this is something, I mean, these are still quite preliminary model results, but this is also something that I have a question about. And especially when we model the neutrally buoyant particle, my guess here is that biofilm formation should eventually be leading to sequestration of that particle into a higher density particle. But actually, based on the model description that we've included right now, this doesn't make a strong difference or an operative difference to the density of the polyethylene when it starts. It has quite a bit lower density than water initially. So I think this is the perfect kind of question actually for investigating with the model framework. How much does the density have to change of the particles due to biofilm formation to make a difference to the export efficiency of polyethylene at the end of a river? I think this is exactly the kind of question that we want, or that I hope the availability of this model framework will spur people to ask, because you can now formulate that into a testable hypothesis and say, we need biofilm to increase the density, the effective density of polyethylene particles by this much. And this is something that then you can test in the field or in the lab to find out if that biofilm formation really is affecting density to that degree. So excellent question. I don't have the perfect answer right now, but I hope that the model gives us the tools for answering the question in a efficient way.